All right, so
This XY plane, we're going to put a circular path in it. So that's what that right there is. And this circular path is going to have some radius r, and there'll be some angle there that is associated with that. And we'll create some point P at that location. And of course, that means that point P has some x location on this axis that's been created, and of course a y position as well. And if we put a force on this thing, and a force that pushes it tangent to the path, so this is basically a lot like the way you open a door. All right, normally you grab the knob and you push straight at the knob, which means you're pushing in a direction that's tangent to the path that the edge of the door takes. Because as you push the door, it swings, it sweeps out an angle because it's hinged. It's on a circular path. Every particle in the door is on a circular path. And if you push straight on the door perpendicular to the face of the door, then it'll follow that circular path. If you push at some other angle, it'll probably still move, but it's harder to move it the closer you get to the hinge or the less that you give a straight push perpendicular to the face of the door. All right, so we always maximize our impact, so to speak, in opening a door if we're closer to the edge, the opposite the hinge of the door, and pushing straight on the door. All right. Now, any force like this is made out of components, so there would be a y component to this force as well as an x component to this force. So again, simple torque, we're heading towards building torque. Torque is forces that produce twisting motion. So wrenches, torque things. Screwdrivers, torque things. Pushing on a door, a hinged thing, is a torque. All right? And so, but it produces rotational motion as opposed to just straightforward linear motion. So now we have a nice abstraction of a very simple everyday process of opening a door. We've mathematized it graphically, and now we're going to mathematize it symbolically. Now, some things to note. This angle theta, alternate interior angles, hope that's ringing a bell. We made you take geometry a few times in your life before here. So we're able to deduce that that angle is theta. And then we can continue and note that this angle right here has to be theta as well. So I'm not going to prove every last piece of the geometry puzzle, but by similar triangles and whatnot, we can make that deduction. And that's going to be helpful because these angles theta are now related to two different things. It's related to lengths that are connected to the application of force, and it's related to the force itself. All right? So that means, and since we're dealing with right triangles, that means we get a few things out of that. So, for instance, sine of theta would equal a number of things. It would equal f of x, f sub x, over the force itself, so opposite over hypotenuse. The cosine of theta would be the y part over the force itself because it's adjacent to the y part. So sine opposite over hypotenuse, cosine adjacent over hypotenuse. You also have, if you go down to the bottom triangle, so down in here, it's also the case that sine of theta is equal to what? It's going to be y over r. And the cosine of theta will be equal to x over r. So we can take these equations. This is just basic trig. The most basic trigonometry there is, right triangle stuff. Okay? This means we get some things out of this. For one, up here with the, this means the x component of force ends up being F sine theta, which is also F times y over r. The y component of the force ends up being F cosine theta, and that's going to be force times x over r. And when we kind of unpack that a little bit more, I can get radius times the x component of force equals y times the force itself, and I also get radius of the times the y component of force equals x times the resolved force itself. So I get a number of equations out of this business. Namely, those four equations are kind of four ways to understand the force here. The most important ones, they're all important, are these right here. We've not had any equations developed yet that relate force and distance in this manner. All right, so let's take a look first at this one right here. All right. The radius is a part of the system. If this is a door, the door has a width. That's going to be its radius, especially if I'm applying a force at the edge of the door. It's full radius where I'm applying the force. But the x component of force, that isn't really there. It's a way for me to abstract a portion of what's actually there. I'm not applying an x and a y force. It's not like I'm somehow managing to do an x force and a y force. I'm applying the force the way I apply it. I'm pushing, okay, straight on. So these x and y forces, they're just sort of out in the Cartesian plane. They're not really there physically in terms of an actual interaction. They're just ways that I can talk about the interaction relative to a frame of reference, namely the xy coordinate plane. Okay, which nobody thinks of that when they open a door, right? It's unless you're weird. Something's wrong there. Then on the other side of the equation, y, again, that's a part of the coordinate system that I'm mathematizing this with, but the force is what I'm actually doing. I'm actually giving it F, right there. I've actually pushed with the F, full force. Not a part of the force that's in the plane, but the actual force, right? So there's this interesting symmetry between mathland stuff that I imposed and an actual thing and they kind of take turns. And both of these equations have that feature to them. In the second one, Fy really isn't there, but the R is. On the other side of that equation, X really isn't there, but the force is, so to speak. So that's that in a nutshell. Now, but wait, there's more. I'm going to redraw this system again, except we're going to apply the force instead of tangent to the path. This force is going to get applied in a way that's consistent with the coordinate system. So we still have, I won't label it, the point P of R there, still have theta. And if I apply the force, this time the force going straight up is actually just going to be the actual applied force. Okay? So the unscripted F in both situations is the applied force, the one that the person or thing is applying to this door that's going to spin. All right? And so we get said this time I'm going to call this length L down here. Instead of X, I'm just going to call it length L. Also, we're going to name this other angle here alpha. And let's talk about the parts. So this force, this applied force F, can come in two parts. Every vector can be written as the sum of two other vectors. Here we're doing it graphically. Okay? Just so you know, this is the right angle part of it. This shorter thing, this is the component of the force that's parallel to R. That's what the double bar, the vertical pipes, meaning parallel to. That's a little math lingo too for that. And then this other one is the force perpendicular to R, the upside down capital T, perpendicular symbol. So force parallel to R, that's in line with the radius, it's parallel to the radius, and perpendicular R, upside down T. Now, alternate, or vertical angles rather, so alpha is right there inside of this triangle. So, which means that this angle up here is theta in the top of this business. It's not going to matter for us really, but there it is. So still the same system of the door, but in this one I'm applying the force differently. I'm not applying it in a way that's tangent to the circular path. I'm applying it in a way that's off the beaten path, so to speak. Right? So its mathematical structure will necessarily be different. And here's how it's different. So the force that's perpendicular to R is going to be F sine alpha, okay, which is the, so look at F perpendicular R in green. It's opposite that angle alpha. So sine of alpha would be the perpendicular part of the force to R over the force itself, or the perpendicular part is F sine alpha. But that's the same as F times L over R, because down here in this triangle I have the same angle alpha, and opposite alpha is the length L, which I'll explain why I went with L instead of X here in a minute, over R. So I have this interesting thing where this sort of, all of this can be written as the force times what's called the lever arm, which is a projection of the radius onto the x-axis in this system, okay, is going to equal the radius times F sine alpha. So we obtain a third equation in this description of a system that has this rotational motion thing going for it. And that lever arm is just basically the distance away from the center of rotation where the force is applied. Just another way to solve the problem. Some problems lend themselves to the top way of looking at things, and some problems lend themselves to the bottom way of looking at things. It really comes down to this. If the force is being applied tangent to the path, we use the top two equations. If the force is otherwise applied to the circular path, we are going to have an easier time with the bottom equation. It's really that simple. Okay? Now, it's a lot to remember. All right? And so we'll be going over various, in fact, today we're going to do a bunch of problems, and we'll do some more next on Monday. And so we're going to do probably 24 problems in this format here in the next week or so to kind of practice all this stuff. But first I need to kind of set it all up. So that's that piece of the puzzle. But we have to continue this game and time write this. You're going to get good at drawing this thing. So as again, this circular path, and we're going to have r and theta, and there'll be this point P. But now we're going to talk about a change in theta. We're going to go from P to Q on this circular path. Well, that means that if I have some point Q up here, also a radius, but I'm going to call this the change in theta. And we'll call that point Q. All right, so this comes with entailments. We have to consider what's happening here. So let's just first let's pay attention to this right here. On that x-axis, those two positions represent a change in x. Okay? I have an x for P, and I have an x for the point Q. And this distance here is actually a negative change in x. Why is it negative? Well, I went from P, x sub P to x sub Q. I went backwards. I went in the negative direction on the x-axis. This is a negative change in x. All right? You'll see why this is important later, because normally it's, oh, it's a delta x. But in what direction? Okay, because we're paying attention to directions here. And if we did a similar thing on the y-axis, we get a delta y here. Of course, this one's positive because we're moving up. We're going from y sub P to y sub Q. So the change in y is a positive one because it's going up, but the change in x is a negative because it's going back. And again, what's going to happen here is these delta x's and y's are going to be associated with angles okay, that are associated with that another aspect of motion in this situation. So far we've dealt with force, the two ways that I could think of force in the last one, and this time I'm going to talk about speed. So there's a linear speed v, okay, that's there, and it would have a vy and a vx. In this system. Now this angle theta shows up here. So theta's here and it's there. That means theta is also there. So this picture gets, this one's a little bit busier than the other ones because we have a change happening here. So so let's do the basic trig. Let's try to entangle all of this. So sine of theta, okay, would be, if I look in the green equation, okay, or not the green equation, but let's pay attention to this stuff going on up here. Sine of theta would have going forward, I could think of sine of theta in terms of speed, but I'm going to think in sine of theta because it opposite of theta, Vx, but the same thing down there on the x-axis would be that delta x, okay? So sine of theta could be written as this negative delta x, because now that I'm sort of pulling the physics away from it, and this is the math side of it. I'm representing because the length of minus delta x is the same as the magnitude of the speed vector for x. Okay, and then that's related to the side PQ. That's the hypotenuse of that thing there. And so this would mean that negative delta x would be minus PQ sine theta, which means delta x would equal minus, and I'm just going to write this and then we'll show it, r delta theta. So first, the easy part is sine theta and y over r. Okay? So sine theta, if I look down here, has this y height to it relative to the r. So I'm stealing from other parts of the puzzle. And why is PQ this distance PQ? How did that become r d theta? So PQ is this straight line right here. The hypotenuse of that green triangle. Why is that an r d theta? Well, it's an arc length. We're really kind of cheating arc length here. So hopefully you remember that arc length was S equals R theta. We did that a while back. You would have done that in your trig or pre-calculus class. That was a prerequisite here. For a small enough change in angle theta, the arc length, the curvy length of the circle, and the straight line distance between them is the same. So when we built the centripetal acceleration formula, we did the same sort of limiting trick in that regard to get this. Okay, so that's the cheat, if you will, coming in there. And so what we get at the end of all this, a strange thing, is that the change in x ends up being negative y change in theta. It's a weird equation. I'm saying that a change in x position is somehow the product of a length y and a change in angle, and it's going to be negative. Okay? So we went from a complicated drawing, okay? We did some trig on parts, and we kind of combined, you know, because they all these parts share the same angle theta, we're able to make these relationships, put this version of the sine relationship into an equivalence relation, equal sign of another version of the sine relationship about the same angle, but about different quantities. So when I have something in common, I get to relate the ways that that something can be encoded for. We do this is one of the main events in all of science, regardless of what science you're paying attention to. So if we go through the same business, you know, cosine of theta will be equal to some stuff, okay? And what that's going to give us at the end of that day is that negative y, delta y, is x delta theta. So we get these two equations that describe how x and y change in relation to how theta changes. We already know that these things are related to, it takes a force to produce these changes in motion. Motion's not going to happen just because it can. Forces produce accelerations, and accelerations produce displacements by changing speed. I just wrapped up all the zeroth laws in one statement. That applies all of the time, whether it's roundy-roundy or straighty-straighty. So all of this trigonometric and geometric wrangling to get these two equations. And what, pray tell, would we do with those equations? That's an excellent question. I'm glad that you asked. Work, total work done, would be the sum of all the force displacement products. And so it would be f of x in the delta x direction plus f of y and the y displacements. And since we're only dealing with a two-dimensional plane, I'll leave it there. But in reality, it would be f sub z times the change in z. Of course, there's no forces directed in the z direction, no displacement, so that term would drop out as 0. So we'll just stick with this right here. Well, let's use this. So work formula, I would have fx, but instead of delta x, for this one, since I'm going round and round here, I would take my delta x from above and use the negative y d theta, and then my f sub y, and I would use that version of delta y, which was x d theta. So total work comes into a different, so notice that they both have a delta theta in common. Since they have a delta theta in common, I can pull that out. And what I'm left with on the inside is an x f y, f sub y, minus a y f sub x. This is strange because I know that work is always, and I'm just setting up some writing space for myself here. This is supposed to be a force, and this is supposed to be a displacement. Well, they are. This is a twisting force, or it's a geometric interpretation of a twisting force. And forces that produce twisting produce angular displacement. So I still have force times distance, conceptually speaking. Except my force now is a twisting force instead of a linear force, and my displacement is angular instead of linear. I've switched the frame of reference from linear systems to angular systems. Obviously, the door is being displaced along a straight line if I choose to look at it that way. We're just not looking at it that way when it comes to rotational energy, because that's not the most interesting or useful part of that kind of motion. All right? So I have this. Well, stop the presses, but work is supposed to equal the change in some sort of kinetic energy. Well, in this case, rotational kinetic energy, the thing we just worked on in the previous lecture. So somehow, all of this has to equal 1/2 I omega squared. So we have a new kid in town. This half I omega squared thing is in equivalence relation with this weird twisting force xfy minus yfx d theta thing. All right? Now, one last thing that I want to put into this, simply because it was shown to you previously in another course, and you probably spent perhaps up to a day working on Kramer's rule. Does that ring a bell with matrices? Determinants. You do a cross product. Okay? You're not allowed to forget this. You signed an oath, a blood oath, that you would never forget Kramer's rule and everything else. You don't remember that either. Okay. So, just real quickly, product can be quite a physical thing as it relates to a geometric understanding of the nature of that twisting force. So the math can make sense of the physical situation, or vice versa, depends how you look at it. Obviously the mathematics is a little tedious, to say the least, but none of the math we did was above your pay grade. This is all stuff you've seen before in algebra or trig or geometry class. None of this is new stuff. What is new is that we have a different conception now of how things relate to one another. So it doesn't really matter much what field you're going into. If you're going into the medical field or the engineering field or chemistry, biology, whatever, it's always the same thing. You have this stands in some sort of relation to that, or this and that are in a relationship. Every time I get some of this, I get some of that. That means there's some sort of product relationship going on, or this relationship is equivalent to that relationship. That's going to be the structure of everything you do scientifically. So though folks that are, say, in a life sciences college physics class, you're not going to reproduce this ever, but if you're doing physical therapy or somehow related to that sort of thing, you know that torque, if you bust a knee or twist an arm, all these joint things, that means there's torque. Torque's the culprit. That knee got torqued. Okay? Whether it got hyperextended or whatever it was, it got torqued. A force was exerted that caused it to move, and it moved too far, too hard, too something. All right? And if it's robots and engineering, it's the same thing. This lever arm's got to lift that thing, move it over here. It takes force, energy, etc., etc. That right? This is kind of pulling vectors into some prior math that you had learned. So if I have a vector for radius, okay, that would just meaning every radius would have some xy position that you could give the end of that radius. And if it's associated, if there's a force associated or applied at that, then it would have x and y components. So we've already shown this graphically several times in a row here. Well, Kramer's rule and you would have seen this in a pre-calc class. Kramer's rule is one way to do matrices, and it's basically this determinant business. So if you have an array like this position array that's in some sort of connection with the force array, or a vector, these two vectors can go into these matrices in this fashion. Hopefully you remember that there is this cross multiplying business. You take this thing here, you multiply it, and then you subtract from it the product here. And we call this is literally a cross product. Well, we just wrote this cross product. I mean, we just went from, the rotational work ended up being xfy minus yfx times the angular displacement, and that also was 1/2 I omega squared. Basically our work energy theorem for rotational motion. So my point here, this mathland thing, we just derived it geometrically. All right? And the cross product relates to when you have quantities that are in some sort of vector quantities in a plane, okay? And we can write this cross product. They're not collinear, that's the idea. So one way to understand them is this way, and literally what you have when you do this, and I need to draw a good picture. I'm going to draw one just like one I'm going to refer you to later. But the we would call this basically this going to that would be the vector r crossed with the vector f, this cross product. And the cross product actually ends up being, the magnitude of the cross product ends up being related to an area. Okay? So if I draw another pretty picture, the cross product can be understood in a geometric way. It can be understood in this matrix mathematical manipulative way, or the cross. So let's imagine that I have some vector r, and in the same plane I'll have some vector f. So that's an xy plane. The reason I drew it this way is I'm about to have a third dimension pop up out of that. So just imagine that f and r are in the same plane, which isn't that the case when you do a wrench or something like that? And ends up being the case that the cross product of these two things, its magnitude is equal to this area. So the magnitude of this cross product actually has a geometric representation in the area that would come from if I basically completed the parallelogram, parallel force vector, parallel radius vector. The area of that space, it will always be the magnitude of the cross product. All right, so often when you compute these torques, you're not likely to do it in its vector form. You're going to most likely use components. The difference would be if you actually have a computing environment where it's tracking all the numbers and you could just let it do the vectors. Your calculators will let you do that. There's a vector mode in all these graphing calculators you have. You could literally type in the full vector form, cross product them, and it would give you this magnitude. It would give you the size of this space. It would tell you how much torque or whatever it is you were working on. So this is just sort of to kind of finish the picture, so to speak, because some additional sort of house cleaning things here to wrap this up. I would like to remind you the zeroth law theorem that we developed a while back said that acceleration times displacement was equal to average speed times the change in speed. That's linear. Well, the ZLT, if I go angular on it, instead of linear acceleration, I have angular acceleration. We use the letter alpha for lots of things. We use it for an angle today. But in terms of acceleration, rotational acceleration is the letter alpha. So I can translate linear to angular by using an angular variable. Instead of linear displacement, it's going to be angular displacement, delta theta. And instead of two v's in an average or a change in speed, it's going to be angular speed, average angular speed, and the change in that. So that's the ZLT, but rotational version of it, or circular you might call it. All right, and this would work out alpha d theta would be 1/2 omega plus omega naught. That's what the average omega is. The delta omega is final minus initial. And once again, I could put 2 alpha d theta equals omega squared minus omega naught squared. And if you recall, this right here, this linear form, this also worked out to 2 ADS equals v squared minus v naught squared. We used that a few times. Every physics textbook in the universe has these two versions of kinematics, linear and rotational kinematics. They don't pitch it in terms of the zeroth law theorem because I'm one of two authors of the zeroth law theorem, and I haven't authored any books yet, so it's therefore not in a book. And of course, this equation's been around longer than me, but it hasn't been around longer than me for the reasons that I give. All right, you can derive it by other means, but they're not physical. They're just another math trick. We derived it because the time to change position is the same as the time to change speed. Okay, so that's why it's a zeroth law theorem, equivalence of time. So what we have here, this is rotational kinematics, these sorts of equations. And every one of the equations, delta S equals V delta T, could change to its angular form. And you have a list like that in your textbook. And up here, this is linear kinematics. Nice thing is that the list of linear kinematics equations, I can rewrite them with angular variables, and I have a list of rotational kinematics. Nothing changes. The structure is identical, but the letter labels change because the nature of the motion changes. But computationally, as long as you stick in radians, you'll always get the right answers using the exact same approach. You just have to change the way that you think about what it is you're looking at. So that's that.